To begin our discussion on electricity, we want to start with the idea of electric charge. There's two objects that we're going to discuss that have electric charge, but these are by no means the only objects that have charge in the universe. We want to talk about the proton and the electron. Those are the most common two that you'll encounter. The symbol for charge is the letter Q. However, when talking about protons in particular, we a lot of times will use this lowercase letter p with the superscript positive. And that's because the proton has a positive charge, and its charge is 1.6 times 10 to the negative 19th coulombs. So when talking about charge, we measure the amount of charge in a unit called coulombs, which we can abbreviate with the letter C, same as meter can be abbreviated with the letter M. The mass of the proton is 1.67 times 10 to the negative 27th kilograms. So it's a very small amount of mass. And the proton is found within the nucleus along with the neutron. The electron, again, charge is abbreviated Q, but electron in particular is the letter E with a superscript negative. And that negative is because the charge of the electron is negative 1.6 times 10 to the negative 19th coulombs. So it has the same magnitude of charge, only it's negative. The mass of the electron is about 2,000 times smaller than the proton. Its mass is 9.11 times 10 to the negative 31st kilograms. And the electron is found somewhere outside the nucleus. Niels Bohr at one point said that they travel in orbitals just like the planets go around the sun. But now we know that we can never tell the exact location of the electron as per the Heisenberg uncertainty principle. All we can say is the most likely location of the electron, which would be in this region of space called the electron cloud. Now, the shape of the electron cloud is based on which electrons we're talking about and which orbital they're in, whether it be the s, the p, the d state, and so forth. So this electric charge, there's two things we can say about the electric charge. And the first thing is we can say it's conserved. Just like energy is conserved, just like momentum is conserved, the electric charge is conserved. And that means that the total amount of charge in a closed system always stays the same. This does not mean that charge cannot be created, nor does it mean that charge cannot be destroyed. We can create charge. We can destroy charge. They're doing so at Fermi Labs, and they're doing so at CERN. One way that we can actually create charge is if we have a nucleus and we have a photon, which is a tiny packet of light, interact with that nucleus. Now, what sometimes might happen is we have a pair production, they say. For instance, we might create an electron. The electron might move in one direction. And what always is created with it, though, because this would be a violation of conservation of charge, is it might also create a positron. And so the two together still has a total charge of 0. So the total charge is still conserved. The amount of charge in the beginning, the amount of charge at the end is conserved, the total. However, we can create those charges. And again, a positron is simply an electron with a positive charge. And so you say, well, how is that not a violation of the conservation of mass? Well, Lavoisier said that mass is conserved only in chemical reactions, and this is a nuclear reaction. What Einstein came up with is that energy is equal to mc squared. So the amount of energy that the photon had, which we can calculate by multiplying Planck's constant times the frequency of the photon, this amount of energy of the photon goes into the goes into the mass of the two electrons. So energy is turned into mass. And this is what Einstein said, that energy and mass are the same thing. Now, the only problem is that once that antimatter comes into contact with regular matter, it's going to annihilate. So they're both going to be destroyed. And so what happens to that mass of the electrons? What happens to all of that mass? Well, it goes back into energy. And so again, energy can create mass, mass can create energy, but the total amount of charge in a closed system must stay the same. So if it's not a closed system, of course charge can be transferred, like if we rub a balloon on our head, charge goes onto the balloon, giving it a negative charge. So charge can stay, but that simply means that the charge of our hair becomes positive by the same amounts. So the total charge in a closed system stays the same, but if we isolate the system, charge can change. Now we also say that charge is quantized. That simply means that charge is a multiple of this 1.6 times 10 to the negative 19th coulombs. So we can possibly have charges of 1.6 times 10 to the negative 19th. We could also have a charge of 3.2 times 10 to the negative 19th coulombs. Those are both multiples of this elementary charge, this 1.6 times 10 to the negative 19th coulombs. Here we have, let's say, 1 proton, and here we have 2 protons, but you cannot have a charge in between. So there is no such thing as having a charge of 2.0 times 10 to the negative 19th, because you cannot have a fraction of this electron or proton, at least for our purposes right now. So again, electric charge is conserved, the total stays the same, and electric charge is also quantized, which means it has to be a multiple of 1.6 times 10 to the negative 19th coulombs.